Hello, welcome to chemistry lesson 4.02, Understanding Electrons. And what we want to talk about here is how are you and an electron similar? Well, why are we doing this? Electrons are subatomic particles. You're never going to see them. So to understand their behavior is to understand something that is abstract, to understand something that, you have to try to kind of get a handle on and to compare it to something in the physical world, I think is one of the best ways to approach it. Let's talk a little bit about how we got to the point of where Bohr was trying to talk about electrons. In the 1890s, a fellow named Rutherford discovered the proton. So they knew protons existed. And about, 5, 10 years later, a fellow named J.J. Thomson did an experiment where he discovered electrons. Now, up until that point, they assumed that protons were kind of scattered through the atom a little bit like raisins in raisin bread. And so nobody really had a good idea of where the electrons were located, but they all knew they had a problem. So we looked at spectra the other day in class, and we have the hydrogen spectrum was the most classic one, and it had the fewest lines. And so scientists figured if they were going to figure it out, it was going to be with hydrogen. So let's redraw the hydrogen spectrum. You probably didn't see this the first purple one because it's really faint. So you have a light purple and you have a dark purple. And then we've got blue. Whoops, well, okay, that's a little bit close. The blue's usually a little further away. And then further away here is red. And to recap, it didn't matter how much energy they put into a tube of an element, they always got the same four lines back. It's a little bit like putting going and cashing a $100 bill in a change machine and always getting back 95 dollars and 4 ones and 4 quarters, and always getting back the exact same amount of change, no matter what you do. Well, for a full understanding, what did we learn in the last lesson about red light versus purple light? Which one has more energy? Pause the video and let you answer this. Okay, the answer here is the violet. So remember, all UV rays or ultraviolet are what give you the sunburn. That's a good tip for remembering who's got the most energy. So we have more energy here. We have less energy here. And we always get these same four lines. And this is true not only for, remember, capital E is energy. So this is more energy and less energy. Every element in the universe releases its own unique elemental spectrum. And so we looked at sodiums, maybe we looked at neons. And scientists can use this to study things that are way across the galaxy. If they see a nebula and it has a certain spectrum, they know, oh, hey, there's a lot of argon in that, or there's a lot of nitrogen in that. But this was a mystery. No one could figure out why. Like if you put in a little energy, 4 lines. If you put in a lot of energy, 4 lines. So the guy who finally took this on, who finally figured it out, was Niels Bohr. We're going to talk a little bit more about him on the next video. So let's use what he figured out and compare that to you climbing a ladder. So we're going to need a picture of a ladder, which means I have to draw. Yikes. And we're going to give ourselves some ground here. And then we're going to do a different kind of ladder. We're going to do a ladder without rungs. And we're going to put you on the ground, and we're going to do an electron. All right. So to start off with, we're going to talk about the similarities between the two. So similarity number 1. When you start, before you climb a ladder, you start from the ground. From the ground. An electron starts from the ground state. So we call the starting point for an electron the ground state. And we define that as, so this is 1 for the electron. Ground state is the location closest to the nucleus. The location closest to the nucleus. When you decide that you want to climb a ladder, so number 2, you need to use your muscles. And you have to put energy into your muscles to get them to contract. So climbing the ladder requires energy and energy input. In this case, for you, your muscles. So climbing the ladder requires energy. So for, again, we said for people, we're talking about muscles. Well, an electron's the same way. We have to put energy in. And we can't, obviously, electrons don't have muscles, but the way that we can put energy into an atom, so you have to put energy into the atom, is through, so we're going to say the same thing. That means ditto, requires energy. But here we're going to put in electricity, which is what we did when we heated up the tubes to produce the spectrum. Or do you remember what we did after the tubes? We stuck some elements into flames to produce their spectrum. You're like, wait, I only saw one color. If you looked at it through a spectrograph, you would have seen the spectrum. So, or heat. But we've got to put energy in. All right, so let's climb. And our electron's going to go up here. So this is step number 2. The next point is you don't particularly want to stay on the ladder, do you? It's not all that comfortable. So your tendency is to get off the ladder. You want to return to the ground. Well, electrons are the same way. They also want to return to the ground. It's more comfortable. It's actually a lower energy level, and everybody, including us, want to be at the lowest energy level. If you have a day off, you don't want to run around your room and pick it up, probably. Probably want to sit on the couch. Well, turns out if you're an electron, the only way to get off the ladder is to, or a human, for electrons' case, is to fall. We could climb down the ladder, but the only way off the atomic ladder is to fall. So if you want to get off, the way down, only way down is to drop or fall. So same thing. Only way down is to drop or to fall. So here we go. And you're going to make a thud. Didn't really hurt yourself. That says thud. Well, here's where the first big difference comes in. So when that electron falls, when we fall, we now give off energy. In the form of sound. So when we fall, we give off energy in the form of sound. Electrons don't have a voice box. So what are electrons going to do? So this guy falls, and we get what does that represent? It represents electromagnetic radiation in the visible light spectrum. So he's falling down one rung, and we're getting a ray of red light. Huh. Okay. So when electrons fall, they give off energy as electromagnetic radiation. That's why we had to learn about the electromagnetic spectrum before we could do this lesson. Well, what if you didn't just climb up one rung? What if you climbed up to the top and then you fell? Your bubble wouldn't look like this. It would probably look like this. Get some swear words in there maybe, and it would be a lot louder. Now I knew I was probably going to have to wrap up around here. I'm out of room, so I'm going to do that. So I'm going to take number 6 and I'm going to come up here. So for us, the further we fall, the louder our sound energy. The further we fall, the louder our sound energy. Can you guess what's going to happen with electrons? So if I take an electron and I fall from here, that's a lot further fall. It can't yell louder, but can it give off higher energy electromagnetic radiation? Sure can. Hey, check that out. Purple, that's higher energy. So the further an electron falls, the higher the electromagnetic radiation energy. Well, so what's going to happen if I fall from the middle? I'm in the middle and I'm fall. There's that blue light. Now, just even me explaining this to you is probably stretching your brain a little bit. Oh, and here's the other part. I almost forgot one of the most important parts. Finally, let's go with blue. The energy is proportional to the distance for both of us in a sense. So you can say, to sum it up, the energy given off is proportional to the distance. The energy given off is proportional to the distance. So for this one's a little tough to use in our analogy, but if you think about it this way, when you climb the ladder, you can't put your foot here. You can't put your foot here. You can't put your foot here because it's a ladder. So your distances, so what's kind of a big deal about this is both on our human ladder and on our atomic ladder, the distances are fixed. The distances are fixed. So an atom, an electron can't fall from here down to ground or from here down to ground. It can only fall from one of the rungs of its atomic ladder. We should call this the atomic ladder. That's why we only get 4 colors, because you can only travel between these distances. You can't, like if you put energy in, it's not like one of those bells at the fair where you hit it and the ringer goes up. It can only go up fixed levels. On a ladder, you can only climb on the rungs of the ladder. You can't put your foot between. So we've got 2 things. We've got the energy given off is proportional to the distance, and the distances are fixed. These 2 things explain this. If I could levitate this electron to here and I'd fall back down, I would get every color of the rainbow, because an electron could go to any point outside. So this is my nucleus down here. I think I mentioned it, but I should have written it. So this is ground state. In a sense, it's close to ground. The ground state is close to nucleus. If I could go to any given point, I would get a continuous spectrum of color. But because I can only go up to these specific levels, the energy I give off when I fall is proportional to those levels. So this led Bohr, the guy who finally figured this out was Niels Bohr. He said electrons exist in fixed distances away from the nucleus. And he called these orbits, because what he envisioned was a nucleus, and then you had an electron and it orbited around the nucleus in this fixed distance. And he was partially right. We're going to learn in a couple of lessons what he was right about and what he was wrong about. But this was huge. I think this is what he won the Nobel Prize for. It explained this, and it explained for every other element. So every element had these orbits, and the electrons could move. They could move between. So we had more than one. So if you've got an orbit here and you've got an orbit here, the electrons could move between these orbits, and they could rise with energy in and fall and give off energy, but they had to stay in the orbits. All right, so that was a huge game changer. And that's a pretty long video lesson. It should give you a little bit of an indication of how important this is going to be on the test. So I want you to please bring any questions that you have into class the next time. We'll do assess an understanding check on this, give you a couple of multiple choice questions, and we'll talk about it some more. But our takeaways are that basically is if we go through our steps again, just like us on a ladder, electrons start from ground state. It requires their energy in to elevate them or to get them to climb. When they fall, they give off energy. They give off in the form of radiation, in this case, visible light. The further they fall, the stronger the radiation, and it's always in specific wavelengths. This led Bohr to realize that these distances are fixed, and it gave rise to his understanding that electrons actually exist in orbits. All right, we'll continue with Bohr's discovery in the next video. Thanks for watching, and have a good day.